Today we're going to finish section 1.2, which was exploration with patterns. Does anybody remember kind of the basic ideas of what we looked at last time? Without looking back, do you remember some of the things we talked about? Anything at all? Nothing? Do you remember one of them? Arithmetic. Fantastic. That is one of the types of patterns we talked about with arithmetic. Specifically, we called them sequences, right? A list of numbers, sequences. We talked about arithmetic. Does anybody remember the other one we talked about? Geometric. Right. Very good. And we talked about being able to find a general term. We talked about inductive and deductive reasoning. And so what we're going to do next is we're going to take a student's work and we're going to see if we can figure out what's going on. All right, so this is our example. A student has done the following, basically. They've got n plus 5 over 5 equals n plus 1. And what we're trying to do is to think about giving a counterexample. So if you remember, counterexample means an example that shows something does not work. And there's usually lots of counterexamples. Not always, but there's usually lots of counterexamples when something does not work. So can you find and create an example where this statement, n plus 5 over 5 equals n plus 1, does not work? What do you think? Okay, so Amanda's telling me maybe if I put in like n equal to 1. Is that right? Yeah. Okay, so we have to pick a number for n to show this doesn't work. So in other words, I'm trying to show that if I take 1 plus 5 and divide by 5, that's the left-hand side. And if I take, I'm going to put a big old question mark in here, and I take 1 plus 1, the right-hand side, that question mark is not an equal sign. That's what we're really trying to show. It doesn't, in fact, equal. So what is the left-hand side going to be? Not a trick question. 6 over 5. You could change it into a mixed number. You don't need to. 6 over 5 will be just fine if we want to think of it that way. What about the right-hand side? 2. And 6 over 5 does not equal to 2. So this, in fact, would be a counterexample. It's just an example that shows that it doesn't work. Can you find an example showing that it does? That's actually a little more restrictive on this one. Somebody said it. 0, that's right, Tiara. 0 actually would make it work, right? Yeah. 0 is often a good counterexample, something that shows something doesn't work. In this case, 0 is actually an example showing it does work. So if you're looking for something that makes it not work and you don't get that to happen, just try a different number, and you'll probably be successful if you keep trying enough, okay? All right, second question about this particular student's work. What reason might you speculate for a student making this conjecture? Do you remember what conjecture means? We talked about that last time too. Okay, so it's their best guess, right? It's what they think is going to happen. So why would a student think that this might be true? Yeah, so they did something maybe like this. Right? What's wrong with that reasoning? What did they forget to do? Say that louder. You have to add in. Okay, that's one. That there are two ways to think of it, and that's exactly one. So in other words, that somehow like there's an n plus 5 and it's all combined first, right? They forgot to do the combining first. There's something else that they could do that avoids the combining, but not in the way they did it. Do you have an idea? Right, so the other way that they could think about it, where they actually use the division first, is that they could recognize that the n divides by 5 as well as the 5 dividing by 5. So they can, in fact, separate it, but it has to be separated in such a way that n is also divided by 5. So could this be rewritten? Yes. It could be written as n over 5 plus 1, but not just n plus 1. So I haven't written any words down here. I've written a couple of equational kind of justifications. let me clarify that when I write that down, my expectation is that you're writing a couple notes to yourself about what's going on. Because when I ask a question like this, for example, like on a test, I'm going to expect language of what you're saying to the student going on. Do you follow? Because if all you're doing is writing this down without language, the student's not going to make heads nor tails of the work that I just wrote down. It's the words that I said along with the writing that down that actually make all of it make sense. Do you guys see what I mean? So keep that in mind as you're working, is that the dialogue that's going on in your head that you would be saying out loud to the student is what you're going to actually write down on a question like this. Okay? Are we all good? Okay. Another thought in this section, this is again a pattern thing. Lots of fun, especially for those of us who are visual people. Something called figurative numbers. These are based on visual or visually geometric patterns. So I don't mean geometric in the sense that it's a geometric sequence. I mean geometric in the sense that it looks like geometry. Okay? You guys with me on that? They're examples that are neither arithmetic nor geometric. Such numbers can be represented by dots arranged in the shape of certain geometric figures. So the first one I'm going to show you is triangular numbers. And I'm going to establish the pattern, and we're going to take a look and think about what the pattern looks like. So our first one is simply a single dot. The next one looks like this array of dots. The next one looks like this array of dots. I'm going to write down one more. So first, do you understand why they're calling it triangular numbers? Yeah, we've got a great visual. Looks like a triangle. There's really nothing special about the triangle being drawn in this way, but we have a visual pattern that's going on. Now, this visual pattern could correspond to counting how many dots are in the pattern. So that's what I'm going to do next. I'm going to actually write down the pattern in terms of the numbers. I'm going to write mine above my sentence here at the bottom just because it's going to give me a little bit more space and because I want to show you something cool in a minute with it. So this is a pattern of 1, 3, 6, 10, and then it keeps going, right? Okay, so a couple of questions. If I asked you to draw the next shape, could you do it? How would it look different than the shapes I already have? What would you do? What would you draw? Yeah, same picture but 5 across the bottom, right? And you sort of build up from 5 across the bottom. Do you know what the next term in the sequence is based on that image in your mind of what you'd be drawing? 15. Why 15, Amanda? Okay, I added 5 more on the bottom row, right? Have the exact same image, but 5 more on the bottom row. What would the next image be? 6 on the bottom row, and then 7 on the bottom row. So every time I'm counting the number of dots, I'm increasing the number of dots by the same number I did before plus 1 more, right? Okay, so let's take a look at this. I actually showed you one of these last time. I'm going to show you 2 more this time. This is our first one. If I take a look at the pattern here, and we've already said it, but I actually have plus 2, plus 3, plus 4, and just for the sake of being able to do one more line here in a minute, I'm going to write in the next term. We already said what it was. It's 15. And then this is plus 5, right? And we can keep going. It'd be plus 6 and plus 7 plus 8. This is not arithmetic. What would be the case if it were arithmetic? Same number would be added every time, and this is not, right? Not. But the pink numbers that I've got up here, what can you tell me about the pink numbers? They are arithmetic. They increase by 1 every time. So what we did is called the first differences. Those pink numbers is called the first differences. If I take the pink numbers and do the process again, and I get them all to match, right, a numerical pattern of those pink numbers, what we would say is that these have a constant, hence the plus 1, second difference. And it wouldn't have to be plus 1, but they all have to be plus the same value or minus the same value. So this one actually has, this is not part of this particular problem, but it's going to help you on a couple other ones in your homework, that's why I'm bringing it up. We would say that this one has a constant second difference. I don't have a generalized equation that I'm going to write down for this. I'm not asking you to be able to do that. There is a pattern you can do that with, but that's not part of this particular problem we're looking at, okay? Any questions more on this one, this triangular numbers? Okay, the next one we're going to look at square numbers. All right, so square numbers are going to start, much like the last one did, with a single dot. And then I'm going to have 4 dots drawn in the shape of a square, indeed. And then I'm going to have, how many dots was this? 9 dots drawn in the shape of a square. Any idea what my next number of dots might be? So if you're saying 12, it's not quite there. It will be 16. So on this one, it isn't just a matter of adding one layer to the bottom, right? It's sort of adding a layer to the bottom and to the right or left-hand side to increase both the length and the width of our shape. I'm not going to draw it, but if you did need to draw the next one, what would you have to do? 25 dots, right? It'd be 5 dots wide and 5 dots tall. All right, the numerical pattern. Well, the first one's 1. What's the second one? 4. And then? And just for the sake of what we're going to do in a minute, the next one would be 25. And we would continue. This one actually has a very nice equation form that you could write down. I'm not going to ask you to do it, but I am going to ask you right now if anybody notices what it is. It'd be n squared. These are all squared numbers, right? Which sort of makes sense because I'm talking about square figurative numbers, right? So then there's a relationship there, obviously. What I do want to show you, though, is something else that's happening like I done the last one. If we looked, instead of thinking about the fact that everything's squaring numbers, at the differences between the values, what do you get when you're trying to go from 1 to 4 in terms of addition? Plus 3. 4 to 9? That's plus 5. 9 to 16? 7. 16 to 25? 9. Do those have a common difference? Like, is 3, 5, 7, 9 a common difference for the first row? Okay, they're similar, but they're not in common. Remember, common difference means they're exactly the same. Okay, arithmetic sequences have a common difference. 1, 4, 9, 16, 25's differences are 3, 5, 7, 9. It's not the same common number, right? So what do we do then? Well, we can actually do the same process again like we did back on the triangular numbers. Now, this particular value that we're adding is what? This is plus 2 every single time, right? So that is called a common difference, right? They're all exactly the same. So the sequence 3, 5, 7, 9 is an arithmetic sequence because the common difference between each of those is 2. So this is your first differences. These are your second differences. What we can say is that this one has a common second difference. I believe you have a homework problem where you do this kind of process, but the common difference doesn't show up until the third common difference. You do the same thing. You just continue the pattern one below until you get the same number that's added across there. Okay? All right, let's take a look at a couple more things. Or one example, a couple more questions on it. This is actually something that for real took place. In fall of 2011, the newly formed Hurley College of Science and Mathematics had a meeting. On the board, the value 3.1415 ... was written, and we were asked to find the next 5 terms in the sequence of numbers. So this is the question posed to you right now. I want you to tell me, what would you say are the next 5 terms in the sequence, and explain why you believe that. So write down what you think will come next after 3.1415. What comes next? It shouldn't say next 5 terms either. It should say next 2 terms. I don't know why that says 5. Just 2 is fine. Make it say next 2 terms.
Like the numbers after the decimal.
Like the number after 5. What's after 5? What's after 5 again here? What would be the next 2 numbers? Okay. What did you guys choose? 1/6. Who chose 1/6? Most of you did. Okay. There's 2 answers at least for what you could choose. 1/6 is one of them. Those of you who chose 1/6, why did you think 1/6? Okay. So you were looking at the 1/4, 1/5, and you decided 1/6 makes sense to come next. So even those of you who didn't pick that, do you see why that would be a legitimate thing that someone might say? Okay? So if you didn't pick that, what did you pick?
I don't know, this could be wrong. I put
6-1. So why 6-1, Caitlin?
because 3 plus 1 is 4, and 1 plus, and then 4 plus 1 is 5. I don't know, that's probably wrong.
Okay, so you were looking at some kind of a summing of certain things, so you're thinking of it more like maybe like a Fibonacci sequence might do something. Okay, I'm not sure quite that it would be the 6-1.
I skipped it.
But the idea of there being some kind of a summation of something going on is not entirely, left field. That's something that we look at and see in sequences. Anybody put anything else? Possibly. It could be. You maybe don't have enough to go on to think maybe what's next. That's possible. Can I show you what most of us put? Most of us put this. Thank you, Tasha. Tasha, why did you put 9-2? Yeah, it's the next 2 digits in the expansion of pi. So why in the world, I told you that this is what most of us put in the room when I was doing this, why would that have been what we thought of instead of what you guys were thinking of? Any thoughts?
Or science.
Math and science? Like maybe we use pi sometimes? Our prior exposure, what we think about more of the time, is going to affect how we look at things, right? Especially with patterns. Agreed? Which one's right? Well, there's not a right answer. Any of these could be fine. It depends on the previous exposure that we're bringing to the situation. The type of reasoning that this kind of a question is asking you to do, and we talked about this last time too, is inductive reasoning. Yes? What does this actually tell you now, though, about inductive reasoning?
It's based on previous knowledge.
Yeah, previous knowledge comes into play. And not only that, but just how you look at things, right? Inductive reasoning can lead to different solutions that may both be accurate, or at least equally likely. You could also say inductive reasoning can lead you to the wrong solution. If I was actually intending or creating some kind of a test question or something like that, where my intent was for the students to write 1/6, and they write something else because they notice some other pattern, I'm quite likely to count it wrong because that's not the pattern I saw, not the pattern I intended, and that's not very good, is it? So it's something to keep in mind when you ask students to do inductive reasoning, is you have to be open to the possibility that they might not necessarily see things the way you do, and it might be okay, and their answer might look different, and it might actually be like legitimate, not just off in left field. Any questions on this one? All right.